Assalamualaikum and greetings everyone. Today's topic is on a closed surface integral. Okay, a closed surface may consist of several surfaces where the boundaries of one surface meet with the boundaries of other surfaces, closing and covering a volume inside. So inside a closed surface, you have a solid. So similar to piecewise surface, evaluating a closed surface integral means evaluating surface integral on each surfaces involved and then adding them up all together. But lucky for us, we don't have to use this technique. We have a theorem called the divergence theorem, or also known as a Gauss theorem, where instead of evaluating f dot unit normal vector ds integrate over sigma, so here sigma is a closed surface, what we do is we evaluate triple integrals where the integrand is the divergence of f. So divergence of f, if you recall, is del dot f. So evaluate or integrate del dot f over solid G, where solid G is the solid enclosed by the closed surface sigma. Okay, let's look at this theorem again. So this is called Gauss theorem, or also known as divergence theorem. Divergence because here we have the divergence of f. So let G be a solid whose surface sigma is oriented outwards if f is equal to this, where P, Q, R, those are the components of f, have continuous first partial derivatives on some open set containing G, and unit normal vector n is outward unit normal on surface sigma, then f dot normal vector ds integrate over closed surface sigma is equal to triple integral over solid G, and the integrand is divergence of f, which is del dot f. So this is called a Gauss theorem or divergence theorem, and you can only apply this for a closed surface sigma. Okay, now let's look at an example. Okay, so as an example, let's solve this example. Sorry. Use the divergence theorem to find the outward flux of the vector field F across the surface of a region that is enclosed by a circular cylinder, x squared plus y squared equals 9, and the planes z equals 0 and z equals 2. Okay. All right, so here our surface sigma is a closed surface because we have z equals 0, the plane z equals 0, and the plane z equals 2. Is that right? Let me see again. Yeah, z equals 2. And we have a cylinder, x squared plus y squared equals 9. Okay, let's sketch those. So here we have, let's say this is 3. Okay, so we have a cylinder, upright cylinder, and it doesn't go up forever because we have z equals 2. Let's say that's a 2. So we have goes here. Okay, so we have on top the plane z equals 2. At the bottom we have z equals 0, and the side is x squared plus y squared equals 9. Okay, so if we do not use Gauss theorem, we have to evaluate 4 surface integral because we have one surface z equals 2, that is one surface, and then we have z equals 0, that is another surface, and for this cylinder you have to partition this into 2. One is the one facing the y-axis, and another is the one facing the negative y-axis. So 4 surfaces altogether, which is quite a lot. Okay, but we don't have to do that. We're going to use the Gauss theorem. Okay, so for the Gauss theorem, first we need to find the divergence of f. Okay, so the divergence of f is, oops. So we need to find the divergence of f. Ya Allah. Okay, which is del dot f. Okay, so del dot f is a scalar. So first the component of del, which is partial x, partial y, partial z dot with a vector field f, which is x cubed I plus y cubed j plus z squared j. Okay. All right, so we have x component with the x component, partial x. We need to find partial x of x cubed. So differentiate x cubed with respect to x. That will give you 3x squared, then plus. Now you find partial y of y cubed. So differentiate y cubed with respect to y. That will give you 3y squared plus now the z component with the z component. Differentiate z squared with respect to z. That will give you 2z. Okay, so using the Gauss theorem, f dot unit normal vector ds over the closed surface sigma is equal to triple integrals del dot f, the divergence of f, integrate over solid G. So here you can see that the closed surface sigma is enclosing a solid inside. So the solid is really a cylinder of radius 3, starting from z equals 0, and then it stops on the plane z equals 2. So it's back to our triple integrals. Okay, so here we already calculated del dot f, which is really 3x squared plus y squared plus 2z. That's 2. Okay, and then we're gonna integrate this over solid G. So now back to triple integrals. So in triple integrals, we have Cartesian coordinates, cylindrical coordinates, and spherical coordinates. So obviously, since our solid is a cylinder, we're going to use cylindrical coordinates. So for cylindrical coordinates, we're going to change x and y in terms of r and theta. So here we have 3. So x squared plus y squared is r squared. Z remain as z, and our dv is really dz r dr d theta. Okay, now let's get the limits for z. As you can see here, z is, you just draw a straight line across your solid parallel to the z-axis. You can see that it starts on z equals 0 plane, and then it stops on z equals 2, which means the limits for z is from 0 to 2. Okay, and then you look at the projection of the solid onto the xy plane. We have a circle of radius 2. A circle of radius 2 a circle of radius 3, meaning that r is from 0 to 3 and theta is from 0 to 2 pi. Okay, so it's back to triple integrals. Okay, now integrate with respect to z first. So here we have 0, 3. So here we have 3r cubed z plus integrate zr with respect, to zr with respect to z, we get rz squared over 2, but 2 over 2 is a 1. Okay, and then replace z with upper and lower limits, which are 0 and 2. Okay, all right, now replacing z with upper and lower limits, we get 6r cubed plus 4r, and then 2 squared is 4. Okay, minus 0, and now we integrate with respect to r and theta. Okay, next integration, the middle integration is with respect to r. So we get 6r to the power 4 over 4 plus 4r squared over 2. And then replace r with upper and lower limits. Okay, what is that? 3 to the power of 4 times, times 3 over 2, and then plus 4 over 2 is 2, and then we have 3 squared, which is a 9, so that would give us 2 279 over 2. And then we have d theta from 0 to 2 pi. So we have 279 over 2, theta 0 to 2 pi. Okay, simplify that, we get 279 pi. Okay, so it's so much easier compared to evaluating for surface integral. Okay, so this is Gauss theorem or divergence theorem. Thank you.